In the last couple of videos, we looked at nucleophilic acyl substitution reactions, including saponification, and a general mechanism for nucleophilic acyl substitutions using a basic nucleophile. Here we're going to continue that general theme by looking at the reaction of Grignard reagents with carboxylic acid derivatives, keeping in mind that Grignard reagents are indeed basic nucleophiles. So we can expect that the mechanism for the reaction that we're looking at here will be similar to the basic anionic mechanisms that we looked at previously, and there will be a little bit of an extra twist here. So let's go ahead and take a look at this particular reaction mechanism. So in this mechanism, what we will do is we are going to start in reacting our Grignard reagent with our carboxylic acid or Ca derivative. We'll do the mechanism for this reaction, and let's use as our specific starting material here, let's go ahead and use, we will use ethyl acetate. So we're going to go ahead and make our carbonyl group there, directly bond to an oxygen and a 2-carbon chain to make ethyl acetate our ester starting material here. Get my spelling right there on ethyl acetate, our ester that we'll start with. And we commonly abbreviate that as ETOAC, by the way, when working with it in the lab. ET standing for ethyl, OAC standing for the acetate. We'll react here with phenyl magnesium bromide. So I'm going to go ahead and draw out my phenyl. That is my aromatic ring that I'm drawing here. Magnesium bromide directly bonded to MgBr, keeping in mind that that bond between magnesium and carbon is so positively polarized on the magnesium and so negatively polarized on the carbon that we can think of that carbon as behaving as a carbanion. We'll do that with 2 equivalents of that, and then we'll go ahead and react with our acid as the second step of this. In the first step, I'm going to also add that we will be using THF as an ether solvent, an aprotic solvent, keeping in mind that anytime we react with a Grignard reagent, we always have to use a solvent that is aprotic, meaning it can't donate a proton to the reaction mixture, because of the fact that protic solvents themselves will react with the Grignard reagents. Since Grignard reagents are basic, if we mix that with a protic solvent, the basic nucleophile base, the Grignard reagent, will rapidly remove a proton from that. So in this Grignard reaction with the carboxylic acid derivative, let's go ahead and continue onward, thinking about what's going to happen in this reaction mechanism. Now, as we continue here, we'll think first about the fact that we have a carboxylic acid derivative reacting with a basic nucleophile. That is our recipe for a nucleophilic acyl substitution reaction. So let's go ahead and do that nucleophilic acyl substitution, following the reaction mechanism under basic conditions, which we have looked at in the last couple of videos. So the first step of that mechanism under basic conditions is always that the anionic nucleophile is going to come in and attack the positively polarized carbonyl carbon. And so I'll go ahead and write that in here as number 1 is that the nucleophile, which is anionic, attacks the positively polarized carbonyl group. And so we can show that happening by taking our Grignard reagent, phenyl magnesium bromide, keeping in mind that we think of that bond between magnesium and carbon as being so highly polarized that we can think of that carbon as having a negative formal charge, so we make the carbon like so. And that carbon now, that it has that lone pair of electrons, comes in, it's going to attack the positively polarized carbonyl carbon, and as a consequence of that, the pi electrons go up onto the oxygen like so, creating a new carbon-carbon bond in this reaction between the phenyl carbon and the carbonyl carbon. So let's go ahead and draw out what results from that. So we have an oxygen anion directly bonded to what was our carbonyl carbon here in the starting material is now this carbon that I've highlighted in red in the starting material, red in the product. That carbon is still directly bonded to our O-ethyl group right here on the reactant side. I'm going to go ahead and draw that out on the product side as well. So we do our O-ethyl group like so. And we additionally, what I haven't filled in here and need to fill in, is that one of these 4 bonds is going to our phenyl group. So I'm going to go ahead and put my aromatic ring in there like so. And I will abbreviate that from here on out as just pH for phenyl. That is our generic abbreviation for an aromatic ring. So now that we have accomplished this, we've gone from our trigonal planar starting material to our tetrahedral intermediate. We follow the general layout of these nucleophilic acyl substitution reactions under basic conditions by reforming the carbonyl as the leaving group leaves. This is the exact same paradigm that we have looked at previously. So lone pair comes down to reform the carbonyl. Leaving group, that's our oxygen atom bonded to the alkyl group leaves. We know that's the leaving group because in our starting material, when we go all the way back to our upper left corner for the starting material, we can always categorize the leaving group as whatever heteroatom and on down the chain there is bonded to the carbonyl. So therefore, we expect that this, what I'm circling in green there, is definitely our leaving group. So we break that away, taking the electrons onto the more electronegative atom, that's the oxygen heteroatom here, as the carbonyl reforms. Let's go ahead from there, and we'll draw out our carbonyl group that is reformed, which is directly bonded to a methyl group. I'm highlighting my carbonyl in pink there to illustrate the same atom that we have all along here in pink. And now that is directly bonded to our phenyl group in this nucleophilic acyl substitution reaction. We also had our O-ethyl group, like so, as a leaving group here in this particular reaction. So now that we have accomplished this, our leaving group has left, and we've created a new carbon-carbon bond there, making this a really powerful reaction for taking simple starting materials and creating relatively complex products. What we can do is we think about now, we've done this nucleophilic acyl substitution reaction. That is the entirety of what I'm highlighting in blue here. In green. And now, we mentioned at the top that we had an excess of 2 units of Grignard reagent to 1 unit of ethyl acetate starting material. Thus far, we've only used one of those 2 units of Grignard reagent. And so we say, well, what could possibly happen next? Is there some additional reaction that we know about that we could piggyback onto this and that we would expect to happen as the next stage of this, something to do with that second unit of the Grignard reagent that we have? Well, in this reaction, our nucleophilic acyl substitution reaction has created a ketone product out of this reaction. And so we have to think back about what we know about how ketones react with Grignard reagents to go on to the next phase of this reaction. And we know from our previous work that ketones or aldehydes reacting with Grignard reagents are going to create a new carbon-carbon bond and an alcohol as the final product of the reaction. And so due to the fact that we have an excess of Grignard reagent available, we can continue this reaction onward beyond nucleophilic acyl substitution and into something else. So we did nucleophilic acyl substitution first. We're done with that, but we have this ketone hanging out, and it's in the presence of Grignard reagent. So what's going to happen then is this. Let's go ahead and draw out our ketone that we created. So we have our carbonyl group directly bonded to our phenyl group there. And we'll bring in the Grignard reagent. I'm going to go ahead and draw that as a lone pair of electrons on the carbon. And then we have our magnesium bromide hanging out here with a positive charge on the magnesium there in this case. And what we will do is bring that lone pair of electrons from the nucleophilic phenyl over. They attack the positively polarized carbonyl right here. That forces the pi electrons up onto the oxygen like so. And so we've created another new carbon-carbon bond by linking this carbonyl group, by linking the phenyl group via a bond here to the carbonyl group. So let's go ahead and draw out the product of this step, which is where in this reaction the nucleophilic phenyl, or the nucleophilic Grignard, to be generic about writing out this step, is going to attack the carbonyl group of our ketone. So we'll go ahead and draw out the product that results from that. So our carbonyl group becomes a carbon-oxygen single bond, like so. Our phenyl group, still hanging out here, is pH. And now that we've brought in another aromatic ring, we have a new bond in blue to another phenyl group. So we've got now 2 phenyl groups directly bonded to what was our carbonyl carbon. I'll highlight that carbon that began as a carbonyl group. I will highlight here for us in pink to emphasize that that carbon is the same one all the way through this entire pathway. Now that we have accomplished this, we have at our carbon that was the carbonyl, we don't have a leaving group anymore. We just have these carbon-carbon bonds, and then we have our single bond here to our oxygen. So there's no way to take the lone pair of electrons and bring them down to remake a carbonyl group here because we have no leaving group bonded to the molecule now. Instead, we just have these carbon-carbon bonds, which are strong and therefore not suitable to break. And so unlike nucleophilic acyl substitution, where after we did the nucleophilic attack up top here in the green box, we then had a leaving group leave as the carbonyl reformed, we can't do that anymore now with this particular stage we have gotten to because all we have are carbon-carbon bonds there. We can't break carbon-carbon or carbon-hydrogen bonds in these reactions. And so what's going to happen then is that this intermediate is just going to hang out in solution until you do the second reaction, the second reagent that we add, which is where we add acid. And the sole purpose of that acid is going to be so that the oxygen has a source of proton to pick up. So we'll go ahead and show that pickup of the proton. So we have our two aromatic rings abbreviated as pH, and now we have OH right here, lone pairs of electrons, and that is our final product of this particular reaction. So what we really have here in this particular case of our Grignard reagent reacting with a carboxylic acid derivative is first, we have nucleophilic acyl substitution. That's everything I put in the green box here. But the product of that nucleophilic acyl substitution is going to be an aldehyde or ketone that can then additionally react with a Grignard reagent using reactions that we learned about in previous chapters where we reacted ketones and aldehydes with Grignard reagents in order to create alcohol products. So the take home of this series of reactions that is going on here is that we have to think holistically about the reactions we have learned throughout Organic Chemistry 1 and 2 to recognize that sometimes the product of a particular reaction can continue to further react with additional reagent that is available. So in this particular case, when we get to the end of nucleophilic acyl substitution, we have to plan on continuing onward here because we have a product that can further react with items available in the reaction mixture. So we need to be on the lookout for that, particularly if we were staging a organic reaction working in a lab to make a drug molecule or something along those lines. We need to be aware of what's happening in the real world, and that is that anything that can react with anything else is going to do so. So as we keep that in mind, we need to take this reaction all the way to the final product, which is going to be what we have there in the lower right-hand corner, where we have created our alcohol product that I've circled in red there.